Good afternoon, everybody. Yeah, we're back with exercise 3.7, and we are encountering this question. First, there is some kind of, discussion, explanations. Since we suffered a little bit, struggled a little bit solving in it in the last video, the last live session. Yeah, there is some vector class. Take a look. Provides random access, updates, head, tail in constant time. A good one. And then then the book goes to recursion and higher order functions, generalizing recursion to higher order functions. And you know these two functions, sum and product. Alright, and then fold right is presented. I'm not going to explain it to you, but here's the signature. You type variables, it receives a list, an accumulator, type B, and a function to be applied to two elements, one of type A, one of type B, the accumulator, and results in the accumulator. Look at this, and then it does a pattern match over the list. If it is empty, you return the accumulator. If it is not empty, it applies the function. Look at this beautiful function. It applies this function f to x, which is the head. Look at this type. Look at this x. Look at this type. Look at this x. Look at this a. You see? And the second argument. This second argument is the recursive call to fold right again, with the tail, the accumulator, and the function. And it goes like this until you reach the end of the list, and then you return ACC. And here is the sum via fold right. Look at this. There is some numbers, the accumulator, the function. This will sum. It will perform the addition of all the numbers in the list. You look at this beautiful expression. And then we are presented with products using or via fold right. And in turn, the accumulator is 1, because this is the identity for product. This is for sum. If you use 0 over here, what do you think it will happen? Think for a while. I kind of get nervous when doing live sessions on. So it's okay if you don't have just think. That's all. All right, more discussion, and look at this. Here it is an expansion, some kind of dissemination of the fold right and some of the elements, and they are suggesting that maybe it is easier to visualize it visualize it as applying over the head and calling full right like this. Now in here you will get 3. Look at this. Then the operator, again full right. Until you hit nil, you return the accumulator 0. Look at this, 0, 0, 0, 0 plus 3, 3 plus 2, 5 plus 1, 6. Look at this note. Well, right must traverse all the way to the end of the list, pushing frames onto the call stack as it goes. Alright, must traverse all the way to the end. Here is some beautiful annotation, syntactic sugar, or alternative notation. Alright. Use this syntax judiciously. And we are right to the question. Can product implemented using full right immediately halt the recursion and return 0.0 if it encounters a 0? Because if you have a collection of elements and one of them is 0, why would you want to go to the end of the list when you know that it is 0 from, let's suppose it's the first element or the second element? You will need to traverse the whole list. This is a question. Why or why not? Consider how any short-circuiting might work if you call full rights with a large list. This is a deeper question which we will return to in chapter 5. Okay, can product implemented using full rights immediately halt? We will say no, as full rights, look at this, how it is implemented. There is no check anywhere, any place. There is no place over here in which